So, at a time in the past, the distance between every location was zero. This is known as the Big Bang. Now, today we are in one galaxy somewhere in the local group in Laniakea supercluster, and for the most part, we see every other galaxy in the universe moving away from us. And if you imagine this is our galaxy, you can imagine, well, what would it look like from, well, we see every galaxy moving away from us because the distance between every galaxy is growing. And you also could convince yourself that a faraway galaxy would be moving faster because there is more space between us and a distant galaxy compared to us and a nearby galaxy. So because there's more space between us and a distant galaxy, there is more space expanding between us and that distant galaxy. Edwin Hubble made two very important contributions to the field of cosmology. In a previous lecture, we said that he discovered that these spiral nebula that people were not sure, are they separate galaxies from us or are they just clouds of material inside our own galaxy? He discovered they were in fact other island universes. Edwin Hubble's other major contribution to astronomy and cosmology is that he discovered galaxies are moving away from us. So he discovered the expansion of the universe. Now, if we look at where the galaxies are, well, the further the galaxy is away from us, the faster it's moving away from us. So this plot over here in the center near the top of the slide, this was Edwin Hubble's original plot of the recession of distant galaxies. Now, a more up-to-date plot, this entire plot that Edwin Hubble made would be just in the lower left corner, right near the bottom. So we've extended with better technology, better photographic equipment on telescopes, we've been able to extend this to all the way to essentially the edge of the universe. Now, the galaxies themselves, it's not like they're actively moving. If you want, you could think of the galaxies as being stationary, but they're just carried along for a ride by the expansion. Kind of like if you were in the middle of the ocean in a life raft and you didn't have any oars or anything to propel you with, you would just be riding along with the currents on the ocean. You would not be actively choosing to go anywhere or moving. You would just be along for the ride. And that's what the galaxies are. The galaxies are just carried along with the expansion. Now, our view of the expansion, to make an analogy, we could imagine what would it like to be an ant that lives on the surface of a balloon while the balloon is inflating. So let's imagine we take a balloon, we're going to put some stickers on the balloon, and then we're going to inflate the balloon. So as we inflate the balloon, all the stickers are going to simultaneously move apart from every other sticker. Now, it's not like any one sticker is in a special location on the balloon. They're all moving apart from each other simultaneously. Now, I want to emphasize that this description we have of an ant living on a balloon is an analogy, and analogies are great for understanding concepts, but they do have a certain limitation. So there's no such thing as the center of the universe. There's no such thing as the center of the surface of a balloon. So let's pretend that the balloon is perfectly spherical. We'll pretend that the knot where it ties isn't really there. So it's just a perfect sphere that is expanding. And we're restricted to live on the surface of a balloon. So there's really no such thing as inside the balloon in this sense. We only know about the surface of the balloon. So every point on the balloon is equivalent because we're assuming it's a perfect sphere. And every point on the surface of the balloon is moving apart from every other point on the surface of a balloon. If you are okay with the balloon analogy, just pretend an infinitely flat sheet that expands into an infinitely flat sheet. Now, what about light traveling through the universe? Well, one example of a wave is a wave of light, and light is a spread out thing on space. So if a light wave is a spread out thing on space and space expands, that light wave itself is going to expand. So we could go potentially from a short wavelength light the background on which that light lives is going to get bigger, so that wavelength of light is going to get longer. And the further away an object is, the more time its light has been traveling towards us until it reached our telescope. Because it's far away, it takes longer for its light to get here. And as a result, the redder that object is going to appear. The reason for that is the wavelength of light increases similarly for all colors. So UV light, which is short wavelength, will stretch into purple light. Yellow light is going to stretch into red light. Red light could stretch into infrared light. Infrared light could stretch into radio waves. So every wavelength of light is going to be stretched to longer and longer wavelengths as the light is traveling through the universe. And those wavelengths of light are going to get longer and longer. So in other words, long wavelength is red, redder and redder. And as a consequence of this, very distant galaxies do actually appear red because their light has been traveling for so long that the light they gave off actually has been stretched into the red and the infrared and the radio part of the spectrum. So every galaxy shown here in these boxes, their light has actually been stretched to be much visibly redder than the other more nearby galaxies in this picture. And in addition to colors of light, absorption lines are going to be redshifted as well. So the sun is a nearby object. The distance from us to the sun is pretty constant. So we could look at some absorption lines from certain elements in the sun. This is the spectroscopy. If you want a review of spectroscopy, there are the background science slides at the beginning of these lectures. But if light comes from a very distant galaxy, that light has been traveling through the universe. The universe has expanded, so the wavelength of those particular colors of light has shifted more towards the red. So this redshift of the spectral line will increase with distance. A nearby galaxy, the light didn't need to travel for too long before reaching us, so that light will only redshift a little bit. While a very distant galaxy, that light has been traveling for a long, long time, so that light will be very heavily redshifted by the time it reaches our telescopes. And if you notice, this is the color of light emitted from a laboratory reference frame. And as we get further and further away, these lines will just shift closer and closer to the red end of the spectrum. Now, one thing you might be wondering right now, what about this picture? If the universe is expanding, why are we still orbiting the sun? Shouldn't our galaxy be pulled apart? The answer to that question is, our sun, we are gravitationally bound to the sun. The stars in our galaxy are gravitationally bound to the rest of the galaxy. So objects in a galaxy cluster will tend to stick together. They are close enough that their gravitational attraction pulling them together is strong enough to overcome the expansion of the universe. But if you look at different galaxy clusters, separate galaxy clusters are far enough away from each other that they tend to become more and more separated by the expansion of the universe. So if you're close to an object, you could stay close to that object by your gravitational attraction. You have to be really far away where there is effectively zero gravitational attraction by that object. Then you will see this effect of being separated from that object as the universe expands. And if we look at a whole lot of different galaxy spectra and stack them in terms of increasing distance, we would see these spectral lines actually move more and more over to the red. So here's a whole lot of galaxy spectra. The closest galaxies are around here near the bottom, and you can actually see these spectral lines moving more and more towards the longer wavelengths as the galaxies get more and more distant. Now, the amount of redshift is related to a galaxy's speed. We talked about that during the background science slides at the beginning of this module. If you know how fast an object is moving away from you, you know how redshifted its light is going to be. So If we know the expansion rate of the universe and we know how fast an object is moving away from us based on looking at spectra and translating the amount of redshift into a speed, we could make an estimate on the distance to that object. We can know how far away that galaxy is. And the Hubble law is what relates the speed a galaxy is moving away from us to the distance to that galaxy. So with the Hubble law, v is the speed of the galaxy moving away from us. That's fairly easy to measure. That's just all you have to do is measure the amount of redshift and then turn that into a velocity. D is the distance to the galaxy, which we want to know. And h0 over here, the h with the subscript 0, is the Hubble constant. So this describes the rate at which the universe expands. So the Hubble Space Telescope's key science mission was to determine the value of h0. So Hubble, it tried to look for Cepheid variables. By looking for Cepheid variable stars, it was able to determine the distance to other galaxies. If you know the distance to other galaxies through an independent method, you could then look at how fast those galaxies are receding away from us. And if you know how fast the galaxies are receding away from us by measuring their redshift, you know how far away they are from measuring the Cepheid variables. You're able to put a constraint on the expansion rate of the universe. And today, through various methods, we are able to constrain the Hubble constant is roughly about 70 kilometers per second per megaparsec. So what we did was we assumed that the stuff that fills the universe is mostly stars, galaxies, and other cold material. But what if this assumption is wrong? What if the universe is mostly filled with other stuff? So instead of this, let's assume that maybe the universe is filled with light and hot, fast-moving particles. Earlier in a previous video, I said that photons and other hot gas will dilute more rapidly than cold material. And again, it's not that the particles dilute, it's their energy dilutes. And that's the important thing that we want to track if we're really being precise. So we plug these into the Einstein field equations, and we still end up at the same result, that there was once a time in the past when the distance between everything in the universe was 0, and this is the Big Bang. So the universe will have different expansion histories depending on the stuff that fills the universe. If the universe is made of mostly hot matter, like fast-moving matter like photons, it will grow according to one rule. If you're curious, it grows as the square root of time. If the universe is mostly cold, slow-moving material, it grows as t to the 2/3 power. And it's possible to demonstrate that by working through some of the math. So the important thing to take away from this slide is if you have different stuff filling the universe, you will get different expansion histories.